somewhat like this. So we calculate the probability, and if we plot that probability not in the form of a straight line, but we need to use some other equation, we will see very soon what that equation is, then it is a gradual process, right? So you see here, people with some of these ratings are not getting any promotions, and then slowly at certain rating they get promotion. So that is a gradual process, and this is how the math behind logistic regression looks. So we are trying to find the odds for a particular event happening, and this is the formula for finding the odds. So the probability of an event happening divided by the probability of the event not happening. So P, if it is the probability of the event happening, probability of the person getting a promotion, and divided by the probability of the person not getting a promotion, that is 1 minus P. So this is how you measure the odds. Now, the values of the odds range from 0 to infinity. So when this probability is 0, then the value of the odds is equal to 0. And when the probability becomes 1, then the value of the odds is 1 by 0, that will be infinity. But the probability itself remains between 0 and 1. Now, this is how an equation of a straight line looks. So y is equal to beta 0 plus beta 1x, where beta 0 is the y-intercept and beta 1 is the slope of the line. If we take the odds equation and take a log of both sides, then this would look somewhat like this. And the term logistic is actually derived from the fact that we are doing this. We take a log of px by 1 minus px. This is an extension of the calculation of odds that we have seen, right? And that is equal to beta 0 plus beta 1x, which is the equation of the straight line. And now from here, if you want to find out the value of px, you will see we can take the exponential on both sides, and then if we solve that equation, we will get the equation of px like this. Px is equal to 1 by 1 plus e to the power of minus beta 0 plus beta 1x. And recall, this is nothing but the equation of the line, which is equal to y. Y is equal to beta 0 plus beta 1x. So this is the equation also known as the sigmoid function, and this is the equation of the logistic regression algorithm. Alright, and if this is plotted, this is how the sigmoid curve is obtained. So let's compare linear and logistic regression, how they are different from each other. Let's go back. So linear regression is solved or used to solve regression problems, and logistic regression is used to solve classification problems. So both are called regression, but linear regression is used for solving regression problems where we predict continuous values, whereas logistic regression is used for solving classification problems where we have to predict discrete values. The response variables in case of linear regression are continuous in nature, whereas here they are categorical or discrete in nature. And linear regression helps to estimate the dependent variable when there is a change in the independent variable, whereas here in case of logistic regression, it helps to calculate the probability or the possibility of a particular event happening. And linear regression, as the name suggests, is a straight line. That's why it's called linear regression, whereas logistic regression is a sigmoid function, and the shape of the curve is S. It's an S-shaped curve. This is another example of application of logistic regression in weather prediction, whether it's going to rain or not rain. Now keep in mind, both are used in weather prediction. If we want to find the discrete values, like whether it's going to rain or not rain, that is a classification problem. We use logistic regression. But if we want to determine what is going to be the temperature tomorrow, then we use linear regression. So just keep in mind that in weather prediction we actually use both. But these are some examples of logistic regression. So we want to find out whether it's going to be rain or not, whether it's going to be sunny or not, whether it's going to snow or not. These are all logistic regression examples. A few more examples. Classification of objects. This is again another example of logistic regression. Now here, of course, one distinction is that these are multi-class classification. So logistic regression is not used in its original form, but it is used in a slightly different form. So we say whether it is a dog or not a dog. I hope you understand. So instead of saying is it a dog or a cat or an elephant, we convert this into saying, so because we need to keep it to binary classification. So we say, is it a dog or not a dog? Is it a cat or not a cat? So that's the way logistic regression can be used for classifying objects. Otherwise, there are other techniques which can be used for performing multi-class classification. In healthcare, logistic regression is used to find the survival rate of a patient. So they take multiple parameters like trauma score and age and so on and so forth, and they try to predict the rate of survival. Alright, now finally let's take an example and see how we can apply logistic regression to predict the number that is shown in the image. So this is actually a live demo. I will take you into Jupyter Notebook and show the code. But before that, let me take you through a couple of slides to explain what we are trying to do. So let's say you have an 8x8 image and the image has a number 1, 2, 3, 4, and you need to train your model to predict what this number is. So how do we do this? So the first thing is, obviously, in any machine learning process, you train your model. So in this case, we are using logistic regression. So, and then we provide a training set to train the model, and then we test how accurate our model is with the test data, which means that like any machine learning process, we split our initial data into two parts, training set and test set. With the training set, we train our model, and then with the test set, we test the model till we get good accuracy, and then we use it for inference, right? So that is typical methodology of training, testing, and then deploying of machine learning models. So let's take a look at the code and see what we are doing. So I'll not go line by line, but just take you through some of the blocks. So first thing we do is import all the libraries, and then we basically take a look at the images and see what is the total number of images. We can display using matplotlib some of the images or a sample of these images, and then we split the data into training and test, as I mentioned earlier, and we can do some exploratory analysis, and then we build our model. We train our model with the training set, and then we test it with our test set and find out how accurate our model is using the confusion matrix, the heat map, and use heat map for visualizing this. And I will show you in the code what exactly is the confusion matrix and how it can be used for finding the accuracy. In our example, we get an accuracy of about 0.94, which is pretty good, or 94%, which is pretty good. Alright, so what is a confusion matrix? This is an example of a confusion matrix, and this is used for identifying the accuracy of a classification model, or like a logistic regression model. So the most important part in a confusion matrix is that, first of all, this, as you can see, this is a matrix, and the size of the matrix depends on how many outputs we are expecting, right? So the most important part here is that the model will be most accurate when we have the maximum numbers in its diagonal. Like in this case, that's why it has almost 93-94%, because the diagonals should have the maximum numbers, and the others other than diagonals, the cells other than the diagonals, should have very few numbers. So here that's what is happening. So there is a 2 here, there is a 1 here, but most of them are along the diagonal. What does this mean? This means that the number that has been fed is 0, and the number that has been detected is also 0. So the predicted value and the actual value are the same. So along the diagonals, that is true, which means that let's take this diagonal, right? If the maximum number is here, that means that like here in this case it is 34, which means that 34 of the images that have been fed, or rather actually there are 2 misclassifications in there. So 36 images have been fed which have number 4, and out of which 34 have been predicted correctly as number 4, and 1 has been predicted as number 8, and another one has been predicted as number 9. So these are 2 misclassifications. cells. Okay, so that is the meaning of saying that the maximum number should be in the diagonal. So if you have all of them, so for an ideal model which has, let's say, 100% accuracy, everything will be only in the diagonal. There will be no numbers other than 0 in all other cells. So that is like a 100% accurate model. Okay, so that's gist of how to use this matrix, how to use this confusion matrix. I know the name is a little funny sounding, confusion matrix, but actually it is not very confusing. It's very straightforward. So you are just plotting what has been predicted and what is the labeled information or what is the actual data. That's also known as the ground truth sometimes. Okay, these are some fancy terms that are used. So predicted label and the actual label, that's all it is. Okay, yeah, so we are showing a little bit more information here. So 38 have been predicted, and here you will see that all of them have been predicted correctly. There have been 38 zeros, and the predicted value and the actual value is exactly the same. Whereas in this case, right, it has, there are, I think, 37 plus 5, 42 have been fed the images. 42 images are of digit 3, and the accuracy is only 37 of them have been accurately predicted. 3 of them have been predicted as number 7, and 2 of them have been predicted as number 8, and so on and so forth. Okay, alright, so with that, let's go into Jupyter Notebook and see how the code looks. So this is the code in Jupyter Notebook for logistic regression. In this particular demo, what we are going to do is train our model to recognize digits, which are the images which have digits from let's say 0 to 5 or 0 to 9, and then we will see how well it is trained and whether it is able to predict these numbers correctly or not. So let's get started. So the first part is, as usual, we are importing some libraries that are required, and then the last line in this block is to load the digits. So let's go ahead and run this code. Then here we will visualize the shape of these digits. So we can see here, if we take a look, this is how the shape is, 1797 by 64. These are like 8 by 8 images. So that's what is reflected in this shape. Now from here onwards, we are basically once again importing some of the libraries that are required, like NumPy and Matplot, and we will take a look at some of the sample images that we have loaded. So this one, for example, creates a figure, and then we go ahead and take a few sample images to see how they look. So let me run this code, and so that it becomes easy to understand. So these are about 5 images, sample images that we are looking at. 0, 1, 2, 3, 4. So this is how the images, this is how the data is. Okay, and based on this, we will actually train our logistic regression model, and then we will test it and see how well it is able to recognize. So the way it works is the pixel information. So as you can see here, this is an 8 by 8 pixel kind of a image, and each pixel, whether it is activated or not activated, that is the information available for each pixel. Now based on the pattern of this activation and non-activation of the various pixels, this will be identified as a 0, for example, right? Similarly, as you can see, so overall each of these numbers actually has a different pattern of the pixel activation, and that's pretty much that our model needs to learn for which number, what is the pattern of the activation of the pixels, right? So that is what we are going to train our model. Okay, so the first thing we need to do is to split our data into training and test data set. Right? So whenever we perform any training, we split the data into training and test, so that the training data set is used to train the system. So we pass this probably multiple times, and then we test it with the test data set, and the split is usually in the form of and there are various ways in which you can split this data. It is up to the individual preferences. In our case here, we are splitting in the form of 23 and 77. So when we say test size as 0.23, that means 23% of the entire data is used for testing, and the remaining 77% is used for training. So there is a readily available function which is called train test split. So we don't have to write any special code for the splitting. It will automatically split the data based on the proportion that we give here, which is test size. So we just give the test size, automatically training size will be determined, and we pass the data that we want to split, and the results will be stored in x_train and y_train for the training data set. And what is x_train? These are the features, right, which is like the independent variable, and y_train is the label, right? So in this case, what happens is we have the input value, which is, or the features value, which is in x_train, and since this is labeled data, for each of them, each of the observations, we already have the label information saying whether this digit is a 0 or a 1 or a 2, so that this is what will be used for comparison to find out whether the system is able to recognize it correctly or there is an error. For each observation, it will compare with this, right? So this is the label. So the same way, x_train, y_train is for the training data set, x_test, y_test is for the test data set. Okay, so let me go ahead and execute this code as well, and then we can go and check quickly what is how many entries are there and in each of these. So x_train, the shape is 1383 by 64, and y_train has 1383 because there is nothing like the second part is not required here. And then x_test shape we see is 414. So actually there are 414 observations in test and 1383 observations in train. So that's basically what these 4 lines of code are saying. Okay, then we import the logistic regression library, and which is a part of scikit-learn. So we don't have to implement the logistic regression process itself. We just call these the function, and let me go ahead and execute that. So that we have the logistic regression library imported. Now we create an instance of logistic regression, right? So logistic regr is an instance of logistic regression, and then we use that for training our model. So let me first execute this code. So these 2 lines. So the first line basically creates an instance of logistic regression model, and then the second line is where we are passing our data, the training data set. Right, this is our the predictors, and this is our target. We are passing this data set to train our model. All right. So once we do this, in this case the data is not large, but by and large the training is what takes usually a lot of time. So we spend in machine learning activities, in machine learning projects, we spend a lot of time for the training part of it. Okay, so here the data set is relatively small, so it was pretty quick. So all right, so now our model has been trained using the training data set, and we want to see how accurate this is. So what we'll do is we will test it out in probably phases. So let me first try out how well this is working for one image. Okay, I will just try it out with one image, the first entry in my test data set, and see whether it is correctly predicting or not. So and in order to test it, so for training purpose we use the fit method. There is a method called fit which is for training the model. And once the training is done, if you want to test for a particular value, new input, you use the predict method. Okay, so let's run the predict method, and we pass this particular image, and we see that the shape is, or the prediction is 4. So let's try a few more. Let me see for the next 10. Seems to be fine. So let me just go ahead and test the entire data set. Okay, that's basically what we will do. So now we want to find out how accurately this has performed. So we use the score method to find what is the percentage of accuracy, and we see here that it has performed up to 94% accurate. Okay, so that's on this part. Now what we can also do is we can also see this accuracy using what is known as a confusion matrix. So let us go ahead and try that as well, so that we can also visualize how well this model has done. So let me execute this piece of code, which will basically import some of the libraries that are required, and we basically create a confusion matrix, an instance of confusion matrix, by running confusion matrix and passing these values. So this confusion underscore matrix method takes two parameters. One is the y underscore test, and the other is the prediction. So what is the y underscore test? These are the labeled values which we already know for the test data set, and predictions are what the system has predicted for the test data set. Okay, so this is known to us, and this is what the system has, the model has generated. So we kind of create the confusion matrix and we will print it, and this is how the confusion matrix looks. As the name suggests, it is a matrix, and the key point out here is that the accuracy of the model is determined by how many numbers are there in the diagonal. The more the numbers in the diagonal, the better the accuracy is. Okay, and first of all, the total sum of all the numbers in this whole matrix is equal to the number of observations in the test data set. That is the first thing, right? So if you add up all these numbers, that will be equal to the number of observations in the test data set, and then out of that, the maximum number of them should be in the diagonal. That means the accuracy is pretty good. If the numbers in the diagonal are less, and in all other places there are a lot of numbers, which means the accuracy is very low. The diagonal indicates a correct prediction. This means that the actual value is same as the predicted value. Here again, actual value is same as the predicted value, and so on, right? So the moment you see a number here, that means the actual value is something and the predicted value is something else, right? Similarly here, the actual value is something and the predicted value is something else. So that is basically how we read the confusion matrix. Now, how do we find the accuracy? You can actually add up the total values in the diagonal. So it's like 38 plus 44 plus 43 and so on, and divide that by the total number of test observations. That will give you the percentage accuracy using a confusion matrix. Now let us visualize this confusion matrix in a slightly more sophisticated way using a heat map. So we will create a heat map with we'll add some colors as well. It's like a more visually more appealing. So that's the whole idea. So let me run this piece of code, and this is how the heat map looks. And as you can see here, the diagonals again are all the values are here, most of the values. So which means this seems to be reasonably accurate. And yeah, basically the accuracy score is 94%. This is calculated, as I mentioned, by adding all these numbers divided by the total test values, or the total number of observations in test data set. Okay, so this is the confusion matrix for logistic regression. Alright, so now that we have seen the confusion matrix, let's take a quick sample and see how well the system has classified, and we will take a few examples of the data. So if we see here, we picked up randomly a few of them. So this is number 4, which is the actual value, and also the predicted value. Both are 4. This is an image of 0. So the predicted value is also 0. Actual value is of course 0. Then this is the image of 9. So this has also been predicted correctly, 9, and actual value is 9. And this is the image of 1. And again, this has been predicted correctly as like the actual value. Okay, so this was a quick demo of logistic regression, how to use logistic regression to identify images.
What is a decision tree? Let's go through a very simple example before we dig in deep. Decision tree is a tree-shaped diagram used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. Let's start with a simple question. How to identify a random vegetable from a shopping bag? So we have this group of vegetables in here, and we can start off by asking a simple question, is it red? And if it's not, then it's going to be the purple fruit to the left, probably an eggplant. If it's true, it's going to be one of the red fruits. Is the diameter greater than 2? If false, it's going to be what looks to be a red chili. And if it's true, it's going to be a bell pepper from the capsicum family. So it's a capsicum. problems that decision tree can solve. So let's look at the two different categories the decision tree can be used on. It can be used on the classification, the true, false, yes, no, and it can be used on regression, where we figure out what the next value is in a series of numbers or a group of data. In classification, the classification tree will determine a set of logical if-then conditions to classify problems. For example, discriminating between three types of flowers based on certain features. In regression, a regression tree is used when the target variable is numerical or continuous in nature. We fit the regression model to the target variable using each of the independent variables. Each split is made based on the sum of squared error. Before we dig deeper into the mechanics of the decision tree, let's take a look at the advantages of using a decision tree, and we'll also take a glimpse at the disadvantages. The first thing you'll notice is that it's simple to understand, interpret, and visualize. It really shines here because you can see exactly what's going on in a decision tree. Little effort is required for data preparation, so you don't have to do special scaling. There's a lot of things you don't have to worry about when using a decision tree. It can handle both numerical and categorical data, as we discovered earlier, and nonlinear parameters don't affect its performance. So even if the data doesn't fit an easy curved graph, you can still use it to create an effective decision or prediction. If we're going to look at the advantages of a decision tree, we also need to understand the disadvantages of a decision tree. The first disadvantage is overfitting. Overfitting occurs when the algorithm captures noise in the data. That means you're solving for one specific instance instead of a general solution for all the data. High variance. The model can get unstable due to small variation in data. Low bias tree. A highly complicated decision tree tends to have a low bias, which makes it difficult for the model to work with new data. Decision tree important terms. Before we dive in further, we need to look at some basic terms. We need to have some definitions to go with our decision tree and the different parts we're going to be using. We'll start with entropy. Entropy is a measure of randomness or unpredictability in the data set. For example, we have a group of animals. In this picture, there's 4 different kinds of animals, and this data set is considered to have a high entropy. You really can't pick out what kind of animal it is based on looking at just the 4 animals as a big clump of entities. So as we start splitting it into subgroups, we come up with our second definition, which is information gain. Information gain. It is a measure of decrease in entropy after the data set is split. So in this case, based on the color yellow, we've split one group of animals on one side as true and those who aren't yellow as false. As we continue down the yellow side, we split based on the height, true or false equals 10, and on the other side, height is less than 10, true or false. And as you see, as we split it, the entropy continues to be less and less and less, and so our information gain is simply the entropy E1 from the top and how it's changed to E2 in the bottom. And we'll look at the deeper math, although you really don't need to know a huge amount of math when you actually do the programming in Python, because it'll do it for you. But we'll look on the actual math at how they compute entropy. Finally, we went over the different parts of our tree, and they call the leaf node. Leaf node carries the classification or the decision, so it's the final end at the bottom. The decision node has 2 or more branches. This is where we're breaking the group up into different parts. And finally, you have the root node. The topmost decision node is known as the root node. How does a decision tree work? Wonder what kind of animals I'll get in the jungle today? Maybe you're the hunter with a gun, or if you're more into photography, you're a photographer with a camera. So let's look at this group of animals and let's try to classify different types of animals based on their features using a decision tree. So the problem statement is to classify the different types of animals based on their features using a decision tree. The data set is looking quite messy and the entropy is high in this case. So let's look at a training set or a training data set. And we're looking at color, we're looking at height, and then we have our different animals. We have our elephants, our giraffes, our monkeys, and our tigers. And they're of different colors and shapes. Let's see what that looks like and how do we split the data. We have to frame the conditions that split the data in such a way that the information gain is the highest. Note, gain is a measure of decrease in entropy after splitting. So the formula for entropy is the sum, that's what this symbol looks like, that looks like kind of like a funky E, of K, where I equals 1 to K. K would represent the number of the different animals in there, where value, or P, value of I would be the percentage of that animal times the log base 2 of the percentage of that animal. Let's try to calculate the entropy for the current data set and take a look at what that looks like. And don't be afraid of the math. You don't really have to memorize this math. Just be aware that it's there and this is what's going on in the background. And so we have 3 giraffes, 2 tigers, 1 monkey, 2 elephants, a total of 8 animals gathered. And if we plug that into the formula, we get an entropy that equals 3 over 8. So we have 3 giraffes, a total of 8, times the log. Usually they use base 2 on the log. So log base 2 of 3 over 8 plus, in this case let's say it's the elephants, 2 over 8, 2 elephants over a total of 8 times log base 2, 2 over 8, plus 1 monkey over a total of 8, log base 2, 1 over 8, and plus 2 over 8 of the tigers, log base 2 over 8. And if we plug that into our computer or calculator, I obviously can't do logs in my head, we get an entropy equal to 0.571. The program will actually calculate the entropy of the data set similarly after every split to calculate the gain. Now we're not going to go through each set one at a time to see what those numbers are. We just want you to be aware that this is a formula or the mathematics behind it. Gain can be calculated by finding the difference of the subsequent entropy values after a split. Now we will try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking that the gain we get out of them. The condition that gives us the highest gain will be used to make the first split. Can you guess what that first split will be just by looking at this image? As a human, it's probably pretty easy to split it. Let's see if you're right. If you guessed the color yellow, you're correct. Let's say the condition that gives us the maximum gain is yellow. So we will split the data based on the color yellow. If it's true, that group of animals goes to the left. If it's false, it goes to the right. The entropy after the splitting has decreased considerably. However, we still need some splitting at both the branches to attain an entropy value equal to 0. So we decide to split both the nodes using height as the condition. Since every branch now contains single label type, we can say that entropy in this case has reached the least value. And here you see we have the giraffes, the tigers, the monkey, and the elephants all separated into their own groups. This tree can now predict all the classes of animals present in the dataset with 100% accuracy. That was easy. Use case, loan repayment prediction. Let's get into my favorite part and open up some Python and see what the programming code and the scripting looks like. In here, we're going to want to do a prediction. And we start with this individual here who's requesting to find out how good his customers are going to be, whether they're going to repay their loan or not for his bank. And from that, we want to generate a problem statement to predict if a customer will repay loan amount or not, and then we're going to be using the decision tree algorithm in Python. Let's see what that looks like, and let's dive into the code. In our first few steps of implementation, we're going to start by importing the necessary packages that we need from Python, and we're going to load up our data and take a look at what the data looks like. So the first thing I need something to edit my Python and run it in. So let's flip on over, and here I'm using the Anaconda Jupyter Notebook. Now you can use any Python IDE you like to run it in, but I find the Jupyter Notebook's really nice for doing things on the fly. And let's go ahead and just paste that code in the beginning. And before we start, let's talk a little bit about what we're bringing in. And then we're going to do a couple things in here. We have to make a couple changes as we go through this first part of the import. The first thing we bring in is numpy as np. That's very standard. When we're dealing with mathematics, especially with very complicated machine learning tools, you almost always see the numpy come in for your numbers. It's called NumPy. It has your mathematics in there. In this case, we actually could take it out, but generally you'll need it for most of your different things you work with. And then we're going to use pandas as PD. That's also a standard. The pandas is a data frame setup, and you can liken this to taking your basic data and storing it in a way that looks like an Excel spreadsheet. So as we come back to this, when you see NP or PD, those are very standard uses, you'll know that that's the pandas, and I'll show you a little bit more when we explore the data in just a minute. Then we're going to need to split the data, so I'm going to bring in our train, test, and split, and this is coming from the sklearn package cross-validation. In just a minute, we're going to change that, and we'll go over that too. And then there's also the sk.tree import decision tree classifier. That's the actual tool we're using. Remember I told you don't be afraid of the mathematics, it's going to be done for you. Well, the decision tree classifier has all that mathematics in there for you, so you don't have to figure it back out again. And then we have sklearn.metrics for accuracy score. We need to score our setup. That's the whole reason we're splitting it between the training and testing data. And finally, we still need the sklearn import tree. And that's just the basic tree function that's needed for the decision tree classifier. And finally, we're going to load our data down here. And I'm going to run this, and we're going to get two things on here. One, we're going to get an error, and two, we're going to get a warning. Let's see what that looks like. So the first thing we had is we have an error. Why is this error here? Well, it's looking at this and it says, I need to read a file. And when this was written, the person who wrote it, this is their path where they stored the file. So let's go ahead and fix that. And I'm going to put in here my file path. I'm just going to call it full file name. And you'll see it's on my C drive, and this is very lengthy setup on here where I stored the data2.csv file. Don't worry too much about the full path because on your computer it'll be different. The data.2csv file was generated by Simplilearn. If you want a copy of that, you can comment down below and request it here in the YouTube. And then if I'm going to give it a name, full file name, I'm going to go ahead and change it here to full file name. So let's go ahead and run it now and see what happens. And we get a warning. When you're coding, understanding these different warnings and these different errors that come up is probably the hardest lesson to learn. So let's just go ahead and take a look at this and use this as an opportunity to understand what's going on here. If you read the warning, it says the cross-validation is depreciated. So it's a warning on it's being removed. And it's going to be moved in favor of the model selection. So if we go up here, we have sklearn.cross-validation. And if you research this and go to the sklearn site, you'll find out that you can actually just swap it right in there with model selection. And so when I come in here and I run it again, that removes a warning. What they've done is they've had two different developers develop it in two different branches. And then they decided to keep one of those and eventually get rid of the other one. That's all that is. And very easy and quick to fix. Before we go any further, I went ahead and opened up the data from this file. Remember the data file we just loaded on here, the data_2.csv. Let's talk a little bit more about that and see what that looks like both as a text file, because it's a comma-separated variable file, and in a spreadsheet. This is what it looks like as a basic text file. You can see at the top they've created a header, and it's got 5 columns, and each column has data in it. And let me flip this over because we're also going to look at this in an actual spreadsheet so you can see what that looks like. And here I've opened it up in the OpenOffice Calc, which is pretty much the same as Excel, and zoomed in, and you can see we've got our columns and our rows of data. A little easier to read in here. We have a result, yes, yes, no. We have initial payment, last payment, credit score, house number. If we scroll way down, we'll see that this occupies 1,001 lines of code, or lines of data, with the first one being a column and then 1,000 lines of data. Now, as a programmer, if you're looking at a small amount of data, I usually start by pulling it up in different sources so I can see what I'm working with. But in larger data, you won't have that option. It'll just be too large. So you need to either bring in a small amount that you can look at it like we're doing right now, or we can start looking at it through the Python code. So let's go ahead and move on and take the next couple steps to explore the data using Python. Let's go ahead and see what it looks like in Python to print the length and the shape of the data. So let's start by printing the length of the database. We can use a simple len function from Python. And when I run this, you'll see that it's 1,000 long. And that's what we expected. There's 1,000 lines of data in there if you subtract the column head. And this is one of the nice things when we did the balanced data from the Panda Read CSV. You'll see that the header is row 0, so it automatically removes a row and then shows the data separate. It does a good job sorting that data out for us. And then we can use a different function, and let's take a look at that. And again, we're going to utilize the tools in Panda. And since the balance underscore data was loaded as a Panda data frame, we can do a shape on it. And let's go ahead and run the shape and see what that looks like. What's nice about this shape is not only does it give me the length of the data, we have 1,000 lines, it also tells me there's 5 columns. So when we were looking at the data, we had 5 columns of data. And then let's take one more step to explore the data using Python. And now that we've taken a look at the length and the shape, let's go ahead and use the pandas module for head, another beautiful thing in the data set that we can utilize. So let's put that on our sheet here, and we have print data set and balance data.head. And this is a pandas print statement of its own. So it has its own print feature in there. And then we went ahead and gave a label for our print job here of data set, just a simple print statement. And when we run that, and let's just take a closer look at that. Let me zoom in here. There we go. Pandas does such a wonderful job of making this a very clean, readable data set. So you can look at the data, you can look at the column headers, you can have it, when you put it as the head, it prints the first 5 lines of the data. And we always start with 0. So we have 5 lines, we have 0, 1, 2, 3, 4 instead of 1, 2, 3, 4, 5. That's a standard scripting and programming set, as you want to start with the 0 position. And that is what the data head does. It pulls the first 5 rows of data, puts it in a nice format that you can look at and view. Very powerful tool to view the data. So instead of having to flip and open up an Excel spreadsheet or open Office Calc or trying to look at a Word doc where it's all scrunched together and hard to read, you can now get a nice open view of what you're working with. We're working with a shape of 1,000 long, 5 wide, so we have 5 columns, and we do the full data head. You can actually see what this data looks like. The initial payment, last payment, credit scores, house number. So let's take this, now that we've explored the data, and let's start digging into the decision tree. So in our next step, we're going to train and build our data tree. And to do that, we need to first separate the data out. We're going to separate it into 2 groups so that we have something to actually train the data with, and then we have some data on the side to test it, to see how good our model is. Remember, with any of the machine learning, you always want to have some kind of test set to weigh it against, so you know how good your model is when you distribute it. Let's go ahead and break this code down and look at it in pieces. So first we have our X and Y. Where do X and Y come from? Well, X is going to be our data, and Y is going to be the answer or the target. You can look at it as source and target. In this case, we're using X and Y to denote the data in and the data that we're actually trying to guess what the answer is going to be. And so to separate it, we can simply put in X equals the balance of the data.values. The first brackets means that we're going to select all the lines in the database. So it's all the data. And the second one says we're only going to look at columns 1 through 5. Remember, we always start with 0. 0 is a yes or no, and that's whether the loan went default or not. So we want to start with 1. If we go back up here, that's the initial payment, and it goes all the way through the house number. Well, if we want to look at 1 through 5, we can do the same thing for Y, which is the answers, and we're going to set that just equal to the 0 row. So it's just the 0 row, and then it's all rows going in there. So now we've divided this into 2 different data sets. One of them with the data going in, and one with the answers. Next, we need to split the data. And here you'll see that we have it split into 4 different parts. The first one is your X training, your X test, your Y train, your Y test. Simply put, we have X going in, where we're going to train it, and we have to know the answer to train it with. And then we have X test, where we're going to test that data. And we have to know in the end what the Y was supposed to be. And that's where this train test split comes in, that we loaded earlier in the modules. This does it all for us. And you can see they set the test size equal to 0.3, so that's roughly 30% will be used in the test. And then we use a random state, so it's completely random which rows it takes out of there. And then finally we get to actually build our decision tree. And they've called it here CLF_entropy. That's the actual decision tree, or decision tree classifier. And in here they've added a couple variables, which we'll explore in just a minute. And then finally, we need to fit the data to that. So we take our CLF entropy that we created, and we fit the X train, and since we know the answers for X train or the Y train, we go ahead and put those in. And let's go ahead and run this. And what most of these sklearn modules do is when you set up the variable, in this case when we set the CLF entropy equal to decision tree classifier, it automatically prints out what's in that decision tree. There's a lot of variables you can play with in here, and it's quite beyond the scope of this tutorial to go through all of these and how they work. But we're working on entropy, that's one of the options. We've added that it's completely a random state of 100, so 100%. And we have a max depth of 3. Now the max depth, if you remember above when we were doing the different graphs of animals, means it's only going to go down 3 layers before it stops. And then we have minimal samples of leaves as 5. So it's going to have at least 5 leaves at the end. So I'll have at least 3 splits, or have no more than 3 layers, and at least 5 end leaves with the final result at the bottom. Now that we've created our decision tree classifier, not only created it but trained it, let's go ahead and apply it and see what that looks like. So let's go ahead and make a prediction and see what that looks like. We're going to paste our predict code in here. And before we run it, let's just take a quick look at what it's doing here. We have a variable yPredict that we're going to do. And we're going to use our variable CLF entropy that we created. And then you'll see .predict. And it's very common in the sklearn modules that their different tools have the predict when you're actually running a prediction. In this case, we're going to put our X test data in here. Now, if you delivered this for use, an actual commercial use, and distributed it, this would be the new loans you're putting in here to guess whether the person's going to be pay them back or not. In this case, though, we need to test out the data and just see how good our sample is, how good of our tree does at predicting the loan payments. And finally, since Anaconda Jupyter Notebook works as a command line for Python, we can simply put the yPredict in to print it. I could just as easily have put the print and put brackets around yPredict in to print it out. We'll go ahead and do that. It doesn't matter which way you do it. And you'll see right here that it runs a prediction. This is roughly 300 in here. Remember, it's 30% of 1,000, so you should have about 300 answers in here. And this tells you which each one of those lines of our test went in there, and this is what our yPredict came out. So let's move on to the next step, where we're going to take this data and try to figure out just how good a model we have. So here we go. Since sklearn does all the heavy lifting for you and all the math, we have a simple line of code to let us know what the accuracy is. And let's go ahead and go through that and see what that means and what that looks like. Let's go ahead and paste this in, and let me zoom in a little bit. There we go. So you have a nice full picture. And we'll see here we're just going to do a print accuracy is, and then we do the accuracy score. And this was something we imported earlier, if you remember at the very beginning. Let me just scroll up there real quick so you can see where that's coming from. That's coming from here, down here, from sklearn.metrics import accuracy score. And you could probably run a script, make your own script to do this very easily. How accurate is it? How many out of 300 do we get right? And so we put in our y test, that's the one we ran the predict on. And then we put in our yPredict in, that's the answers we got. And we're just going to multiply that by 100, because this is just going to give us an answer as a decimal. And we want to see it as a percentage. And let's run that and see what it looks like. And if you see here, we got an accuracy of 93.66667. So when we look at the number of loans and we look at how good our model fit, we can tell people it has about a 93.6 fitting to it. So just a quick recap on that. We now have accuracy set up on here. And so we have created a model that uses the decision tree algorithm to predict whether a customer will repay the loan or not. The accuracy of the model is about 94.6%. The bank can now use this model to decide whether it should approve the loan request from a particular customer or not. And so this information is really powerful. We may not be able to, as individuals, understand all these numbers because they have thousands of numbers that come in. But you can see that this is a smart decision for the bank to use a tool like this to help them to predict how good their profit's going to be off of the loan balances and how many are going to default or not. We're going to be looking at random forest, one of the many powerful tools in the machine learning library. Before we dive into the topic, let's start by looking at a few of the uses for random forest. Currently today it's used in remote sensing. For example, they're used in the ETM devices. If you're a space buff, that's the enhanced thematic mapper they use on satellites. which see far outside the human spectrum for looking at land masses. And they acquire images of the Earth's surface. The accuracy is higher and training time is less than many other machine learning tools out there. Also, object detection, multi-class object detection is done using random forest algorithms. A good example is traffic, where you're trying to sort out the different cars, buses, and things. And it provides a better detection in complicated environments. It's very complicated up there. And then we have another example, Connect. And let's take a little closer look at Connect. Connect, they use a random forest as part of the game console. And what it does is it tracks the body movements and it recreates it in the game. And let's see what that looks like. We have a user who performs a step. In this case, it looks like Elvis Presley going there. That is then recorded so that Connect registers the movement. And then it marks the user based on accuracy. And it looks like we have Prince going on this one. From Elvis Presley to Prince. It's great. So it marks the user based on the accuracy. If we look at that a little closer, we have a training set to identify body parts. Where are the hands? Where are the feet? What's going on with the body? That then goes into a random forest classifier that learns from it. Once we've trained the classifier, it then identifies the body parts while the person's dancing. And it's able to represent that in a computer format. And then based on that, it scores the game and how accurate you are as being Elvis Presley or Prince in your dancing. So why random forest? It's always important to understand why we use this tool over the other ones. What are the benefits here? And so with the random forest, the first one is there's no overfitting. If you use of multiple trees, reduce the risk of overfitting. Training time is less. Overfitting means that we have fit the data so close to what we have as our sample that we pick up on all the weird parts. And instead of predicting the overall data, you're predicting the weird stuff, which you don't want. High accuracy. Runs efficiently on large database. For large data, it produces highly accurate predictions. In today's world of big data, this is really important. And this is probably where it really shines. This is where why random forest really comes in. It estimates missing data. Data in today's world is very messy. So when you have a random forest, it can maintain the accuracy when a large proportion of the data is missing. What that means is if you have data that comes in from 5 or 6 different areas, and maybe they took one set of statistics in one area, and they took a slightly different set of statistics in the other, so they have some of the same shared data, but one is missing like the number of children in the house if you're doing something over demographics, and the other one is missing the size of the house. It will look at both of those separately and build 2 different trees, and then it can do a very good job of guessing which one fits better even though it's missing that data. Let us dig deep into the theory of exactly how it works. And let's look at what is random forest. Random forest, or random decision forest, is a method that operates by constructing multiple decision trees. The decision of the majority of the trees is chosen by the random forest as the final decision. And we have some nice graphics here. We have a decision tree, and they actually use a real tree to denote the decision tree, which I love. And given a random, some kind of picture of a fruit, this decision tree decides that the output is it's an apple. And we have a decision tree 2, where we have that picture of the fruit goes in, and this one decides that it's a lemon. And the decision 3 tree gets another image, and it decides it's an apple. And then this all comes together in what they call the random forest. And this random forest then looks at it and says, okay, I got 2 votes for apple, 1 vote for lemon. The majority is apples, so the final decision is apples. To understand how the random forest works, we first need to dig a little deeper and take a look at the random forest and the actual decision tree and how it builds that decision tree. In looking closer at how the individual decision trees work, we'll go ahead and continue to use the fruit example, since we're talking about trees and forests. A decision tree is a tree-shaped diagram used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. So in here we have a bowl of fruit, and if you look at that, it looks like they switched from lemons to oranges. We have oranges, cherries, and apples. And the first decision of the decision tree might be, is the diameter greater than or equal to 3? And if it says false, it knows that they're cherries because everything else is bigger than that. So all the cherries fall into that decision. So we have all that data we're training. We can look at that. We know that that's what's going to come up. Is the color orange? Well, it goes, orange or red? Well, if it's true, then it comes out as the orange. and if it's false, that leaves apples. So in this example, it sorts out the fruit in the bowl, or the images of the fruit. A decision tree, these are very important terms to know because these are very central to understanding the decision tree and when working with them. The first is entropy. Everything on the decision tree and how it makes a decision is based on entropy. Entropy is a measure of randomness or unpredictability in the data set. Then they also have information gain, the leaf node, the decision node, and the root node. We'll cover these other 4 terms as we go down the tree, but let's start with entropy. So starting with entropy, we have here a high amount of randomness. What that means is that whatever's coming out of this decision, if it was going to guess based on this data, it wouldn't be able to tell you whether it's a lemon or an apple. It would just say it's a fruit. So the first thing we want to do is we want to split this apart. And we take the initial data set, and we're going to create a data set 1 and a data set 2. We just split it in 2. And if you look at these new data sets, after splitting them, the entropy of each of those sets is much less. So for the first one, whatever comes in there, it's going to sort that data and it's going to say, okay, if this data goes this direction, it's probably an apple. And if it goes into the other direction, it's probably a lemon. So that brings us up to information gain. It is the measure of decrease in the entropy after the data set is split. What that means in here is that we've gone from one set, which has a very high entropy, to 2 lower sets of entropy. And we've added in the values of E1 for the first one and E2 for the second 2, which are much lower. And so that information gain is increased greatly in this example. And so you can find that the information gain simply equals decision E1 minus E2. As we're going down our list of definitions, we'll look at the leaf node. And the leaf node carries the classification or the decision. So we look down here to the leaf node. We finally get to our set 1 or our set 2. When it comes down there and it says, okay, this object's gone into set 1, if it's gone into set 1, it's going to be split by some means, and we'll either end up with apples on the leaf node, or a lemon on the leaf node, and on the right it'll either be an apple or lemons. Those leaf nodes, or those final decisions or classifications, that's the definition of leaf node in here. If we're going to have a final leaf where we make the decision, we should have a name for the nodes above it, and they call those decision nodes. A decision node has 2 or more branches. And you can see here where we have the 5 apples and 1 lemon, and in the other case the 5 lemons and 1 apple. They have to make a choice of which tree it goes down based on some kind of measurement or information given to the tree. And that brings us to our last definition. The root node, the topmost decision node, is known as the root node. And this is where you have all of your data and you have your first decision it has to make, or the first split in information. So far, we've looked at a very general image with the fruit being split. Let's look and see exactly what that means to split the data and how do we make those decisions on there. Let's go in there and find out how does a decision tree work. So let's try to understand this, and let's use a simple example, and we'll stay with the fruit. We have a bowl of fruit, and so let's create a problem statement, and the problem is we want to classify the different types of fruits in the bowl based on different features. The data set in the bowl is looking quite messy, and the entropy is high in this case. So if this bowl was our decision maker, it wouldn't know what choice to make. It has so many choices. Which one do you pick? Apple, grapes, or lemons? And so we look in here. We're going to start with a training set. So this is our data that we're training our data with. And we have a number of options here. We have the color, and under the color we have red, yellow, purple. We have a diameter, 331, 331, and we have a label, apple, lemon, grapes, apple, lemon, grapes. And how do we split the data? We have to frame the conditions to split the data in such a way that the information gain is the highest. And it's very key to note that we're looking for the best gain. We don't want to just start sorting out the smallest piece in there. We want to split it the biggest way we can. And so we measure this decrease in entropy, that's what they call it, entropy, there's our entropy, after splitting. And now we'll try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking the gain that we get out of them. The conditions that give us the highest gain will be used to make the first split. So let's take a look at these different conditions. We have color, we have diameter, and if we look underneath that, we have a couple of different values. We have diameter equals 3, color equals yellow, red, diameter equals 1. And when we look at that, you'll see over here we have 1, 2, 3, 4 threes. That's a pretty high selection. So let's say the condition gives us a maximum gain of 3. So we have the most pieces fall into that range. So our first split from our decision node is we split the data based on the diameter. Is it greater than or equal to 3? If it's not, that's false, it goes into the grape bowl. And if it's true, it goes into a bowl full of lemon and apples. The entropy after splitting has decreased considerably. So now we can make two decisions. If you look at, they're very much less chaos going on there. This node has already attained an entropy value of 0, as you can see. There's only one kind of label left for this branch. So no further splitting is required for this node. However, this node on the right still requires a split to decrease the entropy further. So we split the right node further based on color. If you look at this, if I split it on color, that pretty much cuts it right down the middle, and it's the only thing we have left in our choices of color and diameter too. And if the color is yellow, it's going to go to the right bowl, and if it's false, it's going to go to the left bowl. So the entropy in this case is now 0. So now we have 3 bowls with 0 entropy. There's only one type of data in each one of those bowls.